Okay, so let's get started with lecture 16. So again, continuing on wave phenomena. So far in this chapter, we spent a lot of time on transverse waves that travel along a one-dimensional string that's under tension. So we talked about several ways of thinking about waves. So one was the snapshot graph, which is just taking a picture of the displacements at some point in time for various distances, for various positions along the string. We had the related history graph, thinking about the time dependence of the motion of one bit of this string. And then both of these were just different cross sections of a two-dimensional function d of x and t, which describes the displacement as a function of position and time. We found these relationships between them. So we had d of we had d of x and t, this function which can give us both the snapshot figure and the history graph is given by d of x minus vt, where v is the speed of the propagation of the wave. This is for a wave traveling to the right. If you have a wave traveling to the left, v becomes minus v, right? It's a negative number. So if you think of v as the speed, can be d of x plus vt for moving to the left. And we had, for sinusoidal waves, we had the important relationship that lambda is v times t. We also derived some relationships about the physical velocity of different points of the string, and we worked out several examples. So today I want to continue this discussion. So mainly focusing on sound and light, and talk about some quantities that are more specific to sound and light. Okay. So sound, as I mentioned earlier, is a longitudinal wave. But again, one can think of maybe the density of air, right? Which can have compression, so you get a higher density, or rarefaction, which means you have a lower density than kind of the equilibrium uniform density of air. And that's due to the pressure wave that's emitted from a loudspeaker, for example, or a person that's talking. So these air molecules in some regions get compressed together, in some region the density goes down. And again, one can think of maybe the density as the analog of displacement, right? So if you had a wave on a string, you had this transverse displacement, and that was a sinusoidal function of position and time. We can have a similar story. So we can have the density of air, for example, changing as a function of time and space with similar functional form, like a sine omega kx minus omega t plus phi naught. If your sound travels in one direction, so suppose you speak into a cylinder, so the waves just travel inside the cylinder, kind of one-dimensional, instead of propagating in 3 dimensions. And the mathematics of it will become very similar. So we have some speed for the propagation of sound in air. And all the math that we worked out for describing waves can be applied here, where we kind of replace the displacement, say, by density. Okay. Light is also, as we mentioned a few times, is an electromagnetic wave. Again, here you can think of the electric and magnetic fields which are perpendicular to the direction of propagation of light. Again, mathematically, you can describe them by the same functions which should describe transverse waves. So now, for example, the electric field becomes a sinusoidal function of position and time for light that travels in one direction. So you have a laser, for example, that you shine, and it's really parallel rays moving in one direction. You can think about the same mathematical structure that we discussed for transverse waves, mechanical waves along a string, for light. So one important property of light is that it has a speed called the speed of light. It's the fastest speed possible, and it's quite fascinating that it turns out to be independent of the inertial reference frame you're in. And that's really a basis of the special theory of relativity, which we don't discuss in this course. But the speed of light is a constant regardless of what frame you're in. So if you're on the ground or inside a train that's moving, and maybe you have a flashlight, you're standing inside the train, you would measure the same speed of light. Both the observer that's inside the train and the observer that's outside the train. And that has really important implications, and one needs to give up the concept of an absolute time. So it's a quite remarkable fact that the speed of light does not depend on the reference frame. Anyways, so light can be thought of as one small part of the full spectrum of electromagnetic waves. So our eyes, human eyes, are able to see a certain range of wavelength from, let's say, 700 nanometers to 400 nanometers. So 400 would be kind of dark violet, and 700 would be red. And then, of course, it's part of a continuum. So we have ultraviolet radiation, infrared radiation, X-rays, microwaves, various radio waves. And it just happens that our eyes can see within a given range. So as the wavelength goes down, the frequency goes up. All right. Now, one quantity that's quite useful to talk about is something called the index of refraction. So the idea is that light has a particular speed of propagation in vacuum. So which is called c. And then as light moves inside various materials, various transparent or translucent materials that allow light to pass, it typically slows down. So in air, it slows down just a little bit, but in glass, for example, it slows down more significantly. And there is a number which is simply the ratio of c to v, where this is speed of light in a material. And that's a property of that material. So, for example, glass has something like 1.5, right? So the speed goes down by a factor of around 1.5. Diamond has a much higher, it's 2.42. And water is 1.33. So that's, for example, a reason why diamonds can shine and sparkle that much, because if you have a higher index of refraction, as we will see later when we talk about optics, that material is capable of bending light more. All right. So now there is a consequence of this change in the speed of propagation, right? Remember last time we had this example of, let's say, two ropes of different density tied together, and we had a wave that we sent along one of them, and then there was an interface and it entered the other one. So we discussed what happens to the frequency and wavelength in these different mediums. So something very similar happens to light. So again, as light enters, let's say, from vacuum to a piece of glass or some other material that has a given index of refraction, and its speed goes down by a factor of n, its frequency doesn't change. The frequency is a function of the source. And in order for, again, in a very similar way, where we had to have matching displacements at the point of contact between two ropes with different densities, here again at the interface between vacuum and glass, the electric and magnetic fields must match up. So that's only possible if you have the same frequencies, both to the left and to the right of the interface. But a consequence of that is that the wavelength must change as you go through different materials. So this picture is a little bit oversimplified, I would say. First, I mean, you can never just enter and not reflect. There's always something that gets reflected back. And also the amplitude would change. I mean, there are energy conservation considerations here. So it's really just, it's a bit of a cartoon picture just showing one aspect of it, namely the wavelength changing inside. But it's kind of easy to figure out. So lambda is speed divided by the frequency. If the frequency doesn't change and the speed goes down by a factor of n, lambda gets divided by n. You have a smaller lambda that's shortened by a factor of n, the index of refraction of that material, when the wave is traveling inside that material. All right, so here's a question. So the wave fronts you can think of as the positions of the peaks of the maxima. Let's say you have some sinusoidal wave that has peaks and troughs, right? And if you think about the positions of the peaks, for example, those are the wave fronts. So what happens? Which one is correct? So take a few seconds and pause the video, try to figure out the correct answer. All right, so we just argued that as light moves from air to glass, glass has a larger index of refraction than air. The speed of propagation in glass is smaller than the speed of propagation in air. So that means that lambda is v divided by by f, the frequency doesn't change as you go across an interface. V goes down, the speed goes down, so lambda must go down. And the distance between wavefronts is lambda, so in glass, we should have wavefronts that are closer to each other. Okay. So here's again another quick example. So let's go over this together. So we have orange light with a wavelength of 600 nanometers. It's incident on a 1 millimeter thick glass microscope slide. So first, what is the light speed inside the glass? We know the index of refraction in glass, which is 1.5. We know the speed of light in vacuum, which is 3 times 10 to the 8 meters per second. And yeah, you just divide by 1.5 and 5 and you find the speed of propagation in glass. Okay, so how many wavelengths of the light are inside the slide? So we can find the wavelength inside glass, which is the wavelength in vacuum, 600 nanometers, divided by n, the index of refraction of the glass. So that's 400 nanometers. And then how thick is the glass? It's 1 millimeter. So that's 10 to the minus 3, right? That's the thickness. And to see how many wavelengths can fit there, we have to divide the total thickness we have by the length of one full wavelength, which is 400 times 10 to the minus 9, or 4 times 10 to the minus 7, and we find the answer. So far we just talked about waves that propagate in one dimension, right? So the classic example that we started with is just a one-dimensional string, and you can have transverse displacement traveling along it. But in reality, we have more complicated waves, right? So for example, so let's say waves in 2 and 3 dimensions. So in one dimension, let's say we have a source that's performing simple harmonic motion. So it creates these wavefronts, right? So let's think about the sinusoidal wave. So again, that's a snapshot graph. So if you think about the position of all the peaks, you can have this picture of some wavefronts that you see that that are emitted from the source, and then they keep moving along the string at constant speed. So a little bit later, maybe this is here, this is here, this is here, this is here. A little bit later, maybe this has shifted all the way to here, this is all the way here, 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 and then the source puts in a new wavefront. So in the time that the whole snapshot has shifted by 1 lambda, by 1 wavelength, this is, let's say the source just put in 1 wavefront, is at the maximum of its displacement in the positive direction. By the time you shift forward by distance lambda, this has done 1 full cycle, so it's putting in another new wavefront. So that's one picture to think about it. So you have these wavefronts that are put into the medium by the source, and then they just move away in one dimension, right? Away from the source. So let's say that's the x-axis. Now, if you have two-dimensional waves, so suppose you have the surface of water, and there's something that moves up and down at some point on the surface of the water with some harmonic oscillator motion. There's some source that vibrates and puts in oscillations into the surface of the water. So again, as these displacements that you put in propagate away with constant speed, well, they will reach points that are the same distance from the source at the same time, right? That's the statement that the disturbance is traveling away at constant speed. So what are all the points that are the same distance from your source? Well, in 2 dimension, that's a circle, right? So let's say here you have a source. So let's say this source is oscillating with simple harmonic motion with period t, and at time t equals 0, let's say it's at its peak. So we can imagine one wavefront here, and then that one wavefront moves away. And if you've done this for some time, you're going to get a whole bunch of wavefronts separated by distance lambda, right? The distance between all wavefronts, all consecutive wavefronts, will be the wavelength. So we're going to get, depending on, so that's like a 2-dimensional snapshot, if you wish, where instead of showing all the oscillations, we just show the peaks, right? So this is a simplified, let's say, 1-dimensional snapshot for this full snapshot where we just show the peaks, right? And this is a 2-dimensional analog of this. So each wavefront, because the disturbances move away at constant speed, will form a circle. They will be the same distance from your source. So depending at what time you take your snapshot, this distance may not be the wavelength, right? So you can imagine, like, as the waves just begin to emanate, maybe that's very close to the source, but the ones that have propagated for some time, they're all guaranteed to be distance lambda from each other. All of these distances are in the radial direction, right? That's the difference between the radii of these circles. And in 3-dimensional space, well, what happens is, instead of circles, you would get spheres, right? So these wavefronts, the positions of the maxima, the positions of the peaks, become circles that grow at constant speed. They move away from the source, and you will get a whole bunch of concentric circles, all having differences in radii that's equal to lambda, 1 wavelength. So that's a better picture of this. So this is, let's say, the 2-dimensional figure for example, ripples on a pond. You have the source at the center of these circles, and the idea is that the distance between all consecutive circles is lambda. The difference between the radii of all these consecutive circles is lambda. And the first one, well, the central circle has a radius that's between 0 to lambda, depending at what time relative to the time of the oscillations of the source at the center, you take that snapshot picture. So this kind of 1-dimensional effective behavior can emerge from this higher dimensional, let's say 2-dimensional propagation of waves, if you look really, really far away from the source. Right, so if your R becomes very large, so let's go here to the nodes. Very large R, distance from source. So imagine that's the source, that's a huge circle, right, of radius r. And we just look in some local region, right? So you're going to see a very small angular dependence. If r is very large, and you look in a reasonably sized region here, you're not going to see much curvature, right? The difference between all these angles, right, is going to be, so this angle here is just this characteristic perpendicular length divided by r. And if r goes to infinity, for example, the radii become almost parallel, right? So then lambda is some small number a little bit away. So roughly we see these wavefronts in this region that are parallel. And then it seems the wave is just propagating in a one-dimensional line because the direction of propagation is perpendicular to the direction of wavefronts. So that's a limit where effective one-dimensional propagation can emerge from higher dimensional propagation. Okay? So that's another picture. For 3D, the same thing happens, right? If you're in a three-dimensional space and you have these spherical wavefronts, again, as you move really far away from the source and you look in a relatively small region compared to the radius of those circular wavefronts, you would see they're roughly parallel. So you can take the direction perpendicular to these wavefronts, right? So these gray areas are parts of the surface of that spherical wavefront, right? It's a little patch on the surface of this big sphere. And if the patch is much smaller than the size of the sphere, which happens when the sphere is really large, and then you have another sphere whose radius just is larger by lambda, and you have a similar patch on it, you would see these patches that are parallel, and you can neglect the curvature of those patches. So effectively some kind of a one-dimensional wave propagation emerges in that limit. Okay, so how to describe this? Well, let's go back to our note. So looking at this picture, if that's the snapshot, we see that the distance between the different wavefronts is lambda. And then the wavefronts also grow with some speed v. So in general, let's say in 2D, for example, so different points in space now are represented by a two-dimensional vector r, for example. Okay, so how can I write my wave at this point? Well, certainly there's some amplitude which can go down, right? Which does go down because of energy conservation, somehow as a function of r. So if you think about, let's say, the displacement of r and t, it's going to be some amplitude that maybe depends on the length of that vector. But then we can write the same mathematical structure if you think about just the distance between the source and the point we're interested in, right? Along this line, along this radial line, there is no difference between what we see here in terms of having wavefronts that are at a fixed distance and move at a fixed speed between this and the one-dimensional case. So in general, we can write an expression, let's say sine, again, k times r, where r is just the length of this vector, right? Minus omega t plus some phase constant. So when you go to higher dimensional space, what happens is the amplitude changes as a function of how far you are from the source. But then this sinusoidal part can have the same mathematical structure. And again, k is just 2 pi over lambda, and omega is 2 pi over the period, or 2 pi times the frequency. So it turns out that the argument of the sine is quite an important quantity in describing the wave, for reasons that we will see in the next chapter. So when we think about situations where you have multiple sources, and we have this phenomenon of superposition where we add different waves that are generated by different sources, thinking about the argument of that sinusoidal function or this sine is quite useful. So this thing, kx or kr minus omega t plus phi naught, where r is just the distance between the source and the point we're interested in, is known as the phase. And it's of course a function of position and time. Now, if you consider two different points at the same time, then phi naught is the same for them. Omega t is the same if you consider two different points at the same time, which is often what's important in adding waves, right? We add them at the same time. Adding waves, for example, generated by different sources. So there is a quantity known as the phase difference, which is just the difference between these phases, but it turns out to be 2 pi over lambda, or k, times the difference between distances. So consider 2 points at the same time, then let's say we have phase 1, that's kr1 minus omega t plus phi naught. Second phase is kr2 minus omega t plus phi naught. Phase difference is just phi 2 minus phi 1, and that's equal to, these things are the same, right? Omega t and phi naught are the same, so they cancel out. So it becomes k r2 minus r1, which is 2 pi over lambda delta r, where delta r is just r2 minus r1. The difference between the distances of those points from the source. All right. So think for a few minutes about this problem and pause the video when you're ready. Come back and we talk about the answer. Okay, so we have spherical waves traveling outward from a point source. Here, that star is the source. What is the phase difference between the 2 points on the wave marked with dots? So we have one here, we have one here, right? All right. So this one, if I draw, let's say, the circle, to see where it is. It seems to be halfway between these two circles. So it's on a circle that's halfway between this and that. So the difference between the distances, delta r, is just lambda over 2, right? Because consecutive circles, consecutive wavefronts are separated by lambda. So that's lambda over 2. And then 2 pi over lambda times lambda over 2. Lambdas cancel out. It becomes pi, right? 2 pi divided by 2, which is pi. So these 2 points have a phase difference of pi radians. Right? In other words, if at some point in time the sinusoidal part of the displacement for one of them is sine of some angle, for the other one it's sine of the same angle plus pi. All right, so here's an example. So we have a 100 hertz sound wave that travels with a speed of 343 meters per second. That's a typical wave speed for sound in air. And the question is, what is the phase difference between 2 points 60 centimeters apart along the direction the wave is traveling? That's part A. So we have this expression, right? We just found that the phase difference is 2 pi over lambda times the difference in distance. So if the difference in distance is 60 centimeters, we have that. We just need to find lambda, and we know the speed and the frequency. So lambda is the speed divided by the frequency. So we find lambda to be 3.43 meters for 100 hertz. And then we just put it into the expression for the phase difference, and that gives us an answer in terms of radians. Part B is saying how far apart are 2 points whose phase differs by 90 degrees. So 90 degrees is pi over 2 in radians, right? So pi over 2 must be 2 pi delta x over lambda. So delta x over lambda should be a quarter, right? A quarter times 2 gives us 1 over 2. Yeah, and it's just lambda over 4. We again have lambda. We put it in. So that's just a simple check, kind of going back between differences in phase and differences in distance. And the idea is quite simple, right? So one full cycle corresponds to distance lambda and phase difference 2 pi. So 2 pi over lambda is the factor that converts differences in distance to phase difference, and vice versa. If you have the phase difference and you want the difference in distance, you just multiply by lambda and divide by 2 pi. Okay, so the next thing I want to talk about is thinking about energy, power, and intensity in a wave that propagates, let's say in 2-dimensional or in 3-dimensional space more particularly. So first, how do we define power? Power is the rate of change of energy, or the rate that energy kind of passes through a cross section per second. Right? So it has units of joules per second, let's say. And then how do we define the intensity? Well, The intensity is power divided by area. So suppose you have some area, you have a wave that's propagating, and let's say you're really far away for the sake of the argument from the source, so these wavefronts look pretty much parallel. So there's one direction for wave propagation, or you look at a very small patch, so you can basically, it's small enough that it's perpendicular to the direction of propagation at that point. And you want to see how much energy per unit time, that's the power, passes through a unit area of this. So dividing by that gives us the intensity, which is a useful quantity to think about. So let's go back to the notes and think about power and intensity for three-dimensional waves. So power and intensity for 3D waves. Right, so let's say that's our source, and that's a spherical wavefront. Of, let's say, radius r. Okay, so the source is emitting a certain amount of energy per second, right? So what happens is, well, energy is conserved, right? So the energy that enters, let's say, a region here, there's some energy that passes that cross-section at that distance. And there's some energy that passes this cross-section that's bigger, like it's a bigger surface area at a larger distance. So let's say this is R1, this is R2. But if, the energy inside this volume as the wave is just propagating, so the wavefront has reached this, right? It has passed this point, and they just keep coming in and going through. On average, there is no accumulation of energy in the space between them once the wave has already reached and is just passing through. So the power that enters here per unit time, or the energy that enters this spherical surface per unit time, must be the energy that leaves this bigger one per unit time. So there's the total power, the energy per unit time for each of these spheres is the same, and it's how much the source is putting in per unit time. But if you want to think about the intensity, so I1, the intensity for this one, will now be the power, which is a function of the source, divided by 4 pi R1 squared. That's the surface area of sphere. Similarly, I2 will be the total power by 4 pi R2 squared. So we see that the intensity goes down proportional to distance squared, right? So that's, for example, the reason a planet that's very close to the sun, right, gets more energy per its surface area than a planet that's a longer distance from the sun. It's because the intensity of the energy, the light energy coming from the sun, goes down as distance squared, right, as you move far away. That's really just a statement of energy conservation. Yeah, so this is a better picture of what I drew on the notes. The power is just a function of source because energy is conserved. There's no accumulation of energy forever in the medium that supports the propagation of the wave. And therefore the intensity satisfies this equation here. Now, when we think about sound waves, what matters as far as how loud the sound is has to do with its intensity, right? How much energy per unit time it can put per surface area of our eardrum determines how loud we hear that sound. And there's a certain way to describe this. So there's this unit called decibel or decibels, which seems to correlate well with our perception of loudness, if you wish. So therefore, we define this unit like this. So we say if you have a sound of a certain intensity I, we divide that by 1 times 10 to the minus 12 watts per meter squared. So the units of power are joules per second, that's watts, and divided by surface area, that's meters squared. So that's like a characteristic intensity for typical sounds that we hear. And then, so we divide this by that unit. So how many times larger it is than that characteristic intensity I naught. And one takes the logarithm in base 10 and then divides it by 10 decibels. So that's a definition that's quite useful in thinking about light. So this 10 to the minus 12 is at kind of typical mid-range frequencies is the threshold of hearing. So if a sound has lower intensity, you're not going to hear it typically. And then 10 watts per meter squared, which is 13 orders of magnitude larger, is a threshold of pain. So then a sound that's that loud becomes painful. So kind of a logarithmic scale, because it's such a wide range, makes sense, and kind of we get nicer numbers if you put that 10 in front of it. So these are typical examples of decibels for various sounds. So at the threshold, right, if I is equal to I naught, log of 1 is 0, right? Because 10 to the power 0 is going to be 1. So that's convenient, defining it as the log of intensity divided by the characteristic minimum intensity that we can hear basically gives 0 to sounds that we cannot hear, are too low energy that we're not able to hear. And then, there are these numbers just to get a sense of how it is. A person breathing, a whisper, quiet room, outdoors, no traffic. These days, like some dishwashers put decibel grading on how much noise they make. So good ones are like in the 40-something range. Quiet restaurant, normal conversation, busy traffic, and then threshold of pain is 130. So rock concert, stereo at maximum, those are over 100. Okay. So let's get some practice with this. So just as a reminder, decibel was 10 times log base 10 of intensity divided by I naught, and I naught was 10 to the minus 12 watts per meter squared. So pause the video, try to figure out the answer here. All right, so what's happening? So we have this intensity level of one flute that's 70 decibels. And if 10 flutes standing close to each other play, the sound intensity level in decibels will be what? Well, if there's 10 of them, they're putting in 10 times the energy, right? So the intensity should go up by a factor of 10. So practice with so let's say I2 is 10 times I1. I1 is 1 flute, I2 is 10 flutes. So that's what happens to the intensity itself. Okay, so let's say dB1, that intensity in decibels will be written as 10 times log base 10 of I1 divided by I naught. I naught is this particular intensity, the threshold of hearing. And the second one will be 10 log base 10 of 10 I1 I0, right? It's I2, which is 10 times that. So remember, log of xy is log x plus log y. So this just becomes 10 times log 10 base 10 plus log I1 over I naught. Right, so multiplying the intensity by a factor of 10 adds to the decibels, right? Because 10 times this is the original decibel. So here we just get an additional 10 times log 10. And 10 is 10 to the power of 1, so log 10 in base 10 is 1, right? So we should be adding 10 to our decibels. And that's what we do. So 70 goes to 80. So that's a good lesson. Anytime you multiply your intensity by a factor of 10, you make it 10 times larger. You're adding a 10 to your decibels. All right, so let's stop here and we'll continue our discussion of waves in the next lecture.